We're going to have a field day today. Okay, and I'm going to begin with a little outline, okay, so that you can follow along with the subject, what the lecture is about today. Here it is. So this is the rundown. General relativity is known to be inconsistent with quantum mechanics and vice versa, right? Primarily because general relativity does not use force, which is what Newton proposed. It uses something called, it's geometry, as they call it. Gravity is geometry. Why? Because they're saying they have these number lines, and they're going to bend them, and the bending of number lines is what's going to cause gravity. You know, it causes this depression in the number line system in the universe. And it's going to be the field eventually, right? Quantum mechanics deals with force. You know, and what is force? It's a particle. Discrete particle is a force. They have all these particles, these discrete units that they represent force with. And they have all these four forces. There's only two forces we can imagine. One is push, the other one is pull. Those are the only two forces imaginable, forms of contact that we can imagine. And these people invented, perhaps and maybe, you know, two more. They've got the glue arm for the strong force, and they have the weak force. Okay, so aside from the electromagnetic and gravitational one. So they have these four forces of the apocalypse, as I call them, four forces. But general relativity doesn't deal with force at all. Well, they say they don't, but, you know, the question is what pulls down the canvas? When you have all these warped number lines, you know, what's pulling the number lines downwards? Well, you need a force to push that down, and that's where they go back to Newton, I guess. Okay? Anyways, the real difference there, what this causes is that GR, general relativity, is continuous. You know, when you have all these number lines that extend forever, this canvas that they illustrate, that's the mechanism, the physical interpretation. You know, the canvas goes from one edge of the universe to the other, so now you have a certain continuity, and you can more or less try to explain gravity with this thing that touches different objects in different sides of the universe. You can't do that with discrete particles. You know, how does, if you have two particles, I'll put two spoons here. If you have two spoons, how does this spoon touch that one? You know, there's no connection. You got to send something there, and what they send through is from one to the other are these particles, these discrete particles. But by throwing particles, you cannot produce pull, and that's where quantum fails. That's why it doesn't have gravity, and that's why it cannot be reconciled with general relativity. So what did they do? In order to reconcile general relativity and quantum mechanics, they decided to change the quantum nature of quantum mechanics. And you're saying, what do you mean? Yeah, they changed the quantum nature. And for that, we need to know what the word quantum means, okay? And if it fits the new version of quantum, which is really not a new version, what it is that they overthrew quantum mechanics altogether, okay? And now it's called classical mechanics. So quantum mechanics is no longer a theory of quantum, okay? The version we have today, okay? Quantum mechanics is now classical quantum theory. Whenever they put the word classical, it means nobody can pay attention to that anymore. You have classical mechanics, that's studied maybe until high school, and after that they don't touch it anymore. Maybe they touch upon it like a review in college, but in general, you know, it's left behind. Like that's just so you understand what force is, what work is, what energy is in general terms, mathematically, right? But other than that, they don't touch classical mechanics, and that's why they put the word classical, meaning obsolete mechanics. That's what classical means. And now it's classical quantum mechanics, meaning it's obsolete quantum mechanics, okay? And what did they replace it with? They replaced it with quantum field theory, QFT. And what is QFT? What is quantum field theory? Well, they put the word field in there. And it's interesting that the word field is what they have in general relativity. It's a field theory, general relativity. You know, Einstein's equations are field equations. So now we have general relativity with the word field, and now it turns out quantum has the word field, even though quantum is a discrete type of theory. And you need these little balls, these little discrete little units, and somehow they're spreading them out and turning them into this field. And so now they can more or less try to reconcile quantum mechanics with general relativity. Now they're both field theory. So this word field is going to be very critical. We need to know what this word field means, because they're going to use that in both theories. And the point here is that QFT, quantum field theory, is a continuous theory, something that is continuous, that's throughout the universe, or from atom to atom. That's not what quantum was. Quantum originally was discrete, nothing in between. Now they're putting a field in between them and uniting the particles, or affecting two particles at a distance. And so, quantum mechanics is no longer quantum, now it's continuous mechanics. And they call this continuous mechanics quantum field theory. Okay, so that's going to be the general point here. Okay, put it over here. So let's start with well, let me put it back up there so we can follow along. Okay, so what is this? What is this thing that they have there between general relativity and quantum mechanics? Well, relativity, they produce attraction by what? By using a force. That's where they use the force to push down the canvas. What is the canvas made out of? It's made out of number lines. This fishnet is made out of number lines. That's what you're staring at. So they're putting these number lines, meaning it's a mathematical concept that they're bending there, and they produce gravity this way, this weird way. They're saying the reason the Earth doesn't fly out of the solar system is the number lines are warped. That's what they're telling you. Okay, and so they illustrate that everybody can understand what they're staring at, but the explanation doesn't fit this, because what the explanation is that they're bending number lines. Quantum mechanics will have no way of producing attraction with particles, but the way they do it, they have this under the graviton scenario, right, under gravity, they have this little graviton ball that flies from one atom to the other and somehow pulls it. And the way they get away with this is that they put a negative sign in their equation. They say it's negative momentum. That's why it's called negative momentum transfer. Okay? So you can see that these two mechanisms are very different, and they cannot be reconciled. And the way you're going to reconcile them is by putting something between those two particles and turning it into some kind of field, theory, which is what relativity is, a field theory. And now we have a chance of uniting general relativity with quantum mechanics, and that's the goal here. Okay, and so we have here, mathematics. They have discrete particles. Okay, and what's the issue? The issue is that we need to know what this quantum is, because if they're going to introduce the field like ad hoc, does that change quantum at all? I mean, they used to use fields like electric field and magnetic field. What they never had was a gravitational field. But now they're going to use a gravitational field, and one of the things they introduced for that was the Higgs boson, the Higgs field. And that's the mass side of it, but you can see that the counterpart is going to be a graviton field of some kind, and that's where they're going to try to create some kind of field and unite it with general relativity. That's the goal, okay? And so what is a quantum? What do we mean by quantum? Okay, let's start there. It is quantum, quantity or amount. Okay, so it's a specific unit, or you could say, because they were going to replace that with a particle, so they're going to say that this quantity is represented by a ball. That's more or less the situation. That's why they always called it a particle. That's what they've been illustrating, the traveling of one particle from one atom to another, or from one particle to the other. And you can see the dictionary.com is very similar to the Wikipedia. It says quantum, the minimum amount of any physical entity, physical property involved in an interaction. And they have a contradiction there, because entity is not a property. So it's either an entity or a physical property. And what they did, they kind of covered both bases. They said, look, it's a physical entity and it's also a physical property. So that's how they got away with that. Okay, so keep that in mind. They use fancy footwork there, word wizardry to get their stuff through. But yeah, we either have an entity or a property, and it can't be both. And that's where their gods become both objects and concepts. Okay, so Where all this stuff come from? Well, it came from the quantity, quantum, whatever they call it, quantum mechanics, right? Came really from this fellow. His name is Max Planck. And at the beginning of the 20th century, 1900 in fact, towards the end of that year, he wrote a couple papers, and he followed that up with two more in 1901, where he talked about this thing he called the quantum, okay? And it turns out that, which again, it's a minimum amount of a quantity, right? That's all it means. And because they're talking math, not physics, really. But it turns out that this did not become popular, this quantum thing, until Einstein came in 4 years later with his Annus Mirabilis, Miracle Annus, and he made somewhat popular Planck's quantum. Okay, that's where it was. And that's how they got there. And here you can see that it said, this is from someone who wrote there, I've just put it up there, it says, the subject vanished almost completely from the pages of Annals der Physik. For 4 years, no further mention of the word quantum can be found in the pages of this premier journal where Planck had first introduced it. No speculations on its implications until Einstein's revelations of March 1905. Okay, so it's kind of like Einstein made it popular, and that's when the particle notion of light and later on about the electron was put back into mathematical physics. Until then, most of the 19th century, everybody believed in waves, and they thought it was the waves of the ether. The ether was waving. And these people came, beginning of the 20th century, and said, no, light also behaves like particles. And what do they really mean by that? They said, well, light is really energy, whatever that is, and energy comes in discrete packets. And so they had all these energy packets, right, traveling, whatever energy is. And they kind of branched it off and said, look, it's a little ball of energy. And what they're really talking about is not balls. What they're talking about is numbers. They're talking about units, values. That's what they're talking about because they are mathematicians. So they were not doing physics. They were doing mathematics. Okay, so what is QFT? Well, here we have a rundown of that, okay? QFT, what are we talking about? We're talking about replacement of quantum mechanics by, they're replacing quantum mechanics with QFT, with quantum field theory, okay? And that's the first thing you need to note because today they're going to be talking about QFT and not about quantum mechanics anymore, classical quantum mechanics. They kind of left that out, it's obsolete. Q could not explain action at a distance. That's the issue. And it cannot be reconciled with general relativity, which is a field theory. So that's the direction which they took all this. You need a physical mediator to influence distant particle. And if you have all these discrete units, how are you going to influence something at a distance? Well, we had to do something about that. That's what they said. And so they invented this field, okay? Not that they invented it. The field was around, but they said we need to move into the field theory because it gives us two things. First, it gives us a connection between two particles, this extended entity, whatever field is, right? On the one hand, and on the other, we can reconcile it with general relativity. Okay, but what is a field? It's a value at each point in space, meaning that a field is just a bunch of numbers, a bunch of units, a bunch of amounts. And so they're not talking about anything physical, they're talking about mathematics. They're saying, look, every point in space has a value of something, of gravity, of electricity, of magnetism, so it has a certain strength. Yeah, great, that's a description. You haven't explained what that field is. What's the mechanism? And again, they don't have an answer for that. They just say, we're going to put the field in there, and they treat it as a physical object. That's where the crime is committed. Okay, so a field is like a joker in a card game. You can put it anywhere you want, right? And whenever you need to get out of the mess, you say, oh, the field. Just like they use the word energy, they can put it anywhere they want. And it's like, oh yeah, it's energy, whatever that is. They've never defined the word energy. They never defined the word field in a physical sense, right? They just say it's a bunch of numbers. Okay, so what does that tell me? Nothing, because we don't have the physical entity. that we can visualize to understand the mechanism. And field is made of virtual particles. That's important to know. In quantum mechanics, they have all these pseudo particles. They call them virtual particles that pop in very quickly, so quickly that it's unmeasurable. They have them come in from space. The particle is part of space or makes up space, right? Because they have two versions. Either it makes up space or it's contained within space, whatever space is. And the particle just pops in, makes itself known for a certain experiment, meaning the mathematicians have no way of explaining some missing mass, some missing energy, some missing charge, or whatever they're missing. And so they say, oh, the particle came in and went back out again. And so it's ad hoc. The virtual particle is something they need just to fill in the blanks. And all these fields out there, they're made out of these virtual particles. And what is a virtual particle? Is black magic. That's what it's called in science. We call them black magic, witchcraft. These are the old spirits from traditional religions. That's what virtual particle is. It's an ad hoc amount that they need very briefly so that the equation comes out right, meaning that the equation matches observation, meaning whatever the experiment showed, the visible stuff, and then they have the particle go back out again because we weren't able to measure because it left the universe. It's no longer, it disintegrated or went back to being part of space or who knows what. Okay, so the problem is that field is not a thing, not physical. Field is a bunch of numbers by definition. Okay, so let's keep that in mind. It's a mathematical concept, and mathematical concept is not a physical mediator. Okay, so the word field is a terrible word for physics, but they use it in mathematics, in the religion of mathematics, meaning that they're going to be doing some calculations, and they're going to be call that bunch of numbers a field. But then it's when they cross the line and they bring that field into physics, and they say, oh, the field did this and the field did that, that's when they commit the crime. Because if a bunch of numbers, you cannot say that, you cannot bring that into physics and say that I'm going to use a bunch of numbers to move a house. It's like saying I'm going to move a mountain with love. That's great poetically, but you can't use that in physics. Okay, so here's one fellow, his name is Arvin Ash. I talked about him a couple times lately, and he's going to tell us a little bit about this quantum field theory and how it replaced quantum mechanics. So we're going to document this. We're the experts. We're going to bring them the horse's mouth into the picture. We're going to let them tell us what they suggest. Okay, so here's Arvin Ash. Listen to him.
There was a time when everything that happened was seen as random, or a seeming miracle, sometimes attributed to the unseen hand of a divine being. A paradigm shift came through classical mechanics. Every movement and phenomenon could be explained and predicted through observations and equations. There has been one additional, more recent paradigm-shifting development in physics, and that is how quantum mechanics was supplemented and made more complete by quantum field theory, or QFT.
Okay, so they replaced quantum mechanics with this QFT. That was the paradigm shift, and nobody noticed it, and it's a big shift because what people don't realize is they got rid of quantum mechanics. Suddenly it became obsolete because quantum mechanics is per excellence the discrete, the world of the discrete units, right? And field is exactly the opposite. Okay, and so let's address a couple issues raised by Arvin Ash, and here's one of them. Okay, in the old days they explained with miracles, but we haven't changed that at all in mathematical physics. What they have today is explanations which are irrational. So the explanations are still miraculous, you could say, right? They're even worse. In the old days they had these miracles, they had these spirits and angels come in. Today they have all these concepts like field and energy, moving things around, and that's where they become irrational. And they use undefined mathematical concepts. You don't find a definition for the word mass You don't find a definition for the word energy, meaning in terms of physics, okay? Because they're going to use these as physical entities. And these words are really concepts, mathematical concepts, and they have several definitions or several notions. So they use whichever one they need for whatever purpose they have, at hand. And what they do, they reify these concepts and then they move them around. So that's the first one. So, Arvin Ash, he's kind of laughing at the old people of all the old religions, saying, "Oh, yeah, these people used to believe in miracles." Well, these people believe in irrationalities. That's even worse. Yeah, you're better off believing in miracles, I think. Okay, that's the first part. Now let's answer another of his questions. He says, equations explain. No, equations don't explain. They can't explain. An equation is just a description. 1 + 1 = 2 doesn't explain anything. It's just a tautology. That's essentially what it is. E = mc², it doesn't explain anything either. You haven't explained anything with that. You're just saying you turned love into intelligence times velocity of light squared. That's all you did. You haven't explained the mechanism. Science is explanations, and science requires physical interpretations, why the universe works as it does. And what these people think is that you're just going to describe it and get away with it. Why? Because mathematics can only describe. That's the issue. And the final issue I want to comment on regarding his presentation there is QFT did not really supplement QM. What it did, it destroyed it completely. It destroyed the quantum. Okay. Quantum is a discrete entity, and QFT is a continuous entity, mediator. Okay, so in other words, a field. And what is a field? Just a value at each point in space, meaning it's just a concept. It's not even a mediator, but that's how they use it. And so, and the purpose of that was to explain action at a distance. That's what they're all bent on today. That's why quantum field theory has become so popular among the new wave of mathematical physicists, because they cannot explain action at a distance, so they had to move into quantum field theory, the field part especially. Okay, another error that this fellow said, I mentioned that last week, but Arvin Ash, and that is he thinks that science has something, or physics, has something to do with proof and truth. And no, and he said that you need to falsify a theory, otherwise, so anytime he says, someone asks, where's the proof? I know I'm dealing with a non-scientist. But he's saying that it can only be falsified, and falsification is a form of proof. What they're saying is that I'm going to prove to you that you have an error in your theory or whatever. And all he's done with that is saying that he's going to try to convince you of something. That's called falsification. He's going to try to convince you that of something that's wrong. And if you don't believe him, well, you continue believing that it's right. That's all it is. And that's called proof to you, not proof to him. And so again, proof is a matter of opinion. Okay? So when these people introduce these words like truth and fact and proof to shove it down their theory down your throat, that's when they commit the crime. And falsification comes from Karl Popper, it's proof. It is a proof. Falsification means I'm going to convince you that you're wrong. I falsified your theory. But you say, hey, you did. I don't agree with you, and I continue to believe in my theory. And so what was the point of that? It means that this falsification is just a matter of proof. Okay? And so all these scientists that go to college, they learn this falsification thing, and they think they've invented something new. They haven't. It's the same old, same old. It's people shoving down your throat their theory, and we don't do that in science. In science, we explain the mechanism. You go out, you think whatever you want. Nobody cares. Even science doesn't care. Science only cares that you present the mechanism for your consideration, and then you look at it and you say, okay, I believe it or I don't believe it. That's fine. You can reach whatever conclusion you want. But to say that I'm going to shove it down your throat and say, I want you to believe it because I proved it, and you can't falsify it or whatever, that's religion. That part is religion. Okay, so here's another fellow, and he starts off on the wrong foot. His name is Sean Carroll. He's also a popular expert, called expert with quotations there, right? He's called to do a lot of presentations on quantum mechanics and on general relativity. And it turns out he starts out with quantum mechanics by saying that he doesn't understand it. So here we have a theory that all these people talk about, and they all tell you in your face that they don't understand it. So let's hear that first. Okay, here it goes. Listen carefully.
Quantum mechanics, an incredibly successful phenomenology, a set of rules that fits the data to wonderful precision, and yet it makes no sense. You can't quite make sense of it.
Okay, so here they all believe in quantum mechanics, and nobody understands it. Great. In fact, here, just in case, you might say, well, he doesn't understand. No, here you have a forefather of his name is Dick Feynman, and he said the same thing. Well, you understand what I'm going to tell you. You think I'm going to explain it to you so you can understand it. No, you're not going to be able to understand it. You see, my physics students don't understand it either. That is because I don't understand it. Nobody does. While I am describing to you how nature works, you won't understand why nature works that way. But you see, nobody understands that. I can't explain why nature behaves in this peculiar way. And so, nobody understands quantum mechanics, and I'll tell you why, because you can't run the universe with discrete particles. And it's part of the reason they had to move into the field aspect of quantum mechanics, known as quantum field theory, and somehow, without anybody noticing, quantum mechanics became classical quantum mechanics. Means it just became obsolete overnight. Okay, so here we have Carol again. He's going to tell us a little more about this field thingy. Okay, let's find out what he has to say about that. Listen carefully. Here he goes.
Is light, for example, a particle or a wave? A wave is sort of a vibration in a field. So what's the answer to this? This is the answer. It's fields. It's not a mystery. They always tell you that question. They never tell you the answer. You need to stop thinking of the world in terms of particles. You need to start thinking of it in terms of fields. There are particles in the world. No, there aren't. That's the secret that we physicists have never told you, but here I am, I'm going to tell you right now. The world is made of fields, but quantum mechanics says when you look at the world, you don't see it directly. So the reason you think that there are particles is because there are actually all of these fields filling empty space. At every point in space, there's dozens of little vibrating fields in front of you. But quantum mechanics says that when you look at the fields closely enough, they resolve into individual particles. Quantum mechanics says you look at that light very carefully and it turns into individual particles called photons. Photons are the particles that you see when you look at a wave in the electromagnetic field. The reason why light resolves into photons is because quantum mechanics says that when you look at it, that's what you see. The relationship between particles and fields is that fields are what the world is made of, particles are what you see. So the atoms in this table, the electrons, the quarks, the protons, these are all vibrations in fields. There's a quark field that is vibrating. You look at it, you see quarks. There's an electron field that is vibrating. There's a neutrino field that is vibrating. There's a gravitational field that is vibrating, and so on and so on. That's quantum field theory. It is the very heart, the central organizing concept of modern physics.
The only thing you forgot to put the cornfields and the marijuana fields. Yeah, so they deal with these fields, but what is a field? A bunch of numbers. But see, they turn them into physical objects, and everything that you were staring at, all those vectors, those are quantities. And they have these arrows, and they say, look, all these arrows, they form a field. And you say, well, what are those little arrows? Engine arrows on the engines shooting at the army or something? No, those arrows are vectors. What is a vector? Magnitude and direction according to mathematical physics. So you were staring at something that they illustrated, but that illustration is misleading because they're putting arrows for values. Okay, so keep that in mind every time you see one of these arrow thingies. Okay, and that's what they call a field. Okay, but you can see that they think that light is a field, and obviously they're going to say that gravity is a field. That's what QFT is trying to figure out. Okay, how they're going to turn this field into a gravitational field so they can reconcile it with general relativity. And so what is a field? Let's find out. Same person here. We have good old Carol, Sean Carroll. He's going to tell us what a field is. Listen carefully, because now we're going to find out finally what a field is.
Imagine there is a field filling the universe. And what that means mathematically is just that at every point in space there's a number, the value of the field. And this idea of a field turns out to be quite useful. And that's what we do these days. We talk both about particles and about fields. So particles and fields are the two things that physicists talk about when we talk about the ingredients that make up reality. In one sense, a particle and a field are the opposite of each other, right? A particle is something that is one location. Here's the particle, it's nowhere else. A field is the opposite of that. A field is everywhere. At every point in space, there is a value of the field.
Note that he says there's a value of the field. He doesn't say, this is a field here, this little thingy. No, he's saying we have a value of the field. So there's not a ball there. What you have is a number there, okay? Keep that in mind. And so, okay, we have these particles and we have the field. Particle now belongs to quantum mechanics. The field belongs to quantum field theory. And so what was this particle? Because he's saying that particle is just vibration of the field, a local vibration of the field. Okay, so he's got this little canvas that's vibrating locally, and he calls that a particle. Okay, so now we have particle is no longer this ball, this discrete ball. Now it's part of the field that forms the field, and the way it forms this field, at least the way they illustrate it, is this two-dimensional thingy that pops up as a bump, and it's vibrating. It's part of all this vibration all around, and that the entire vibration of all these pieces of this canvas, that's what the field is, the whole thing, the whole shebang. So now let's ask another expert. What is this particle thingy? I mean, everybody should know what a particle is. We learn this in, kindergarten? You know, they don't you play with blocks in kindergarten? You should learn what a particle is. One of the first words you learn is that's a thing, an object, a particle, whatever. Okay, and here we have this lady, Sabine Hassenfelder, and let's see what she says about what a particle is. Let's listen to her very carefully.
What is a particle? Well, I'd say particle physicists know pretty well what particles are. I have to admit that when I would have to answer this question, I'd say, well, a particle it's an irreducible representation of the Poincaré group. So I think that the way that I think about those questions, what is this or what is that, is what's the mathematics that we use to describe this thing. And so I'm not sure that science can even answer the question beyond that. Like, what could possibly answer the question, what a particle is, beyond this mathematical construct that we use to describe it? I don't know.
Standard model
Describes it. Does it represent it? I don't know. It's the best we can do.
It's the best that they can do. They can't do any better. They don't know what a particle is. Again, kindergarten stuff. I don't know, did Sabine ever go through kindergarten? Here, let me show her what a particle is. This is what a particle is, okay? It could be a corpuscle. You can think of it as a round ball. It could be a cube also, for that matter. And there you see a grain of sand. That's known as a particle also. A speck of dust, a little piece of dust that you find on the floor, that's called a particle. And you have the smallest insect known to man, a fairy fly. And there I show it very big, but if you see it very little, it could look like a particle also. I mean, a particle is just a little dot out there, a physical dot. And she goes and she says it's something about the Poincaré group. She doesn't know what a particle is, and she studied in college, I guess, particle physics, meaning quantum mechanics. What do they accelerate in the accelerators? Don't they accelerate particles, or are they accelerating numbers? Are they accelerating vectors? Is that what they're accelerating? pieces of the field. Here you have this vibration of the field locally, right? This bump in the field, and that's the local vibration. Is that what they're accelerating? The bump is moving from one place to another. I mean, try to imagine it. It's even unimaginable because they're talking about numbers. They're not talking about physical things. And again, and that's the reason they don't understand it. That's the reason they cannot explain it. So where do we end with all this? This quantum field theory. Well, I saw a couple of one article there that I liked quite a bit, and it kind of puts the icing on the cake today. And here it is. It's that people think that science is not about explaining. They think that science is about beauty and art. So here's the beauty part. Okay, it says the following. This is from the conversation run by one of the United Kingdom universities. It says the following: encoded in a set of neat compact equations was the idea that our universe is constructed from a sort of magical mesh, now known as space-time. The structure of this mesh would be revealed in the bending of light around distant stars. Physicists had long known that light travels in straight lines. In 1919, observations of a solar eclipse revealed that light does indeed bend. Okay, so we're going to have bent light. Okay, it's no longer running straight. Gravity is going to twist it or bend it or whatever. The extreme elegance of his equations, meaning Einstein, right? How could something so beautiful not be right? So they're saying that science has, or physics has something to do with beauty. That if it's beautiful, it's a beautiful equation, then it's got to be right. It's got to be truth. Okay, fact. And Paul Dirac, one of the mathematical physicists of the 1930s, would later sum up our mathematical descriptions of nature. Beauty is truth, and truth is beauty. And so what these people are looking for is beauty. And they're saying if it's beautiful, whatever beauty, I mean, how can an equation be beautiful? And they say 1 + 1 = 2. Well, that's so beautiful. It must be true. Well, it is true, but what's it got to do with beauty? 1 + 1 = 2 is beautiful. Okay. I think women are beautiful, but to say 1 + 1 = 2 is beautiful, I don't know. And this is the art part. It says, a quest for beauty has been a part of tradition of physics throughout its history. Symmetry, harmony, a sense of unity and wholeness. These are some of the ideals general relativity formalizes. Where quantum theory is a jumpy, jazzy mashup, general relativity is a safe, stately waltz. Okay, so we have jazz versus waltz here. So I guess that's where the art comes in. We applaud the theory not only as a visionary piece of science, but also as an artistic triumph. Okay, so now we're talking about beauty and art. Okay, what do we mean by the word art? A poet noted that the duty of artists everywhere is to what? Enchant the conceptual landscape. Enchant. So we're going to be enchanting you with magic. Bewitching you, as she says in the next line. It says, artists contribute something bewitching to our mental experience. It may not be the duty of scientists to enchant, or bewitch, I guess, our conceptual landscape, yet that is one of the goals science can achieve. No scientific idea has been more enrapturing than Einstein's general relativity. Though he advised there'd never be more than 12 people who'd understand his theory, as with many conceptual artworks, you don't have to understand all of relativity to be moved by it. Okay, so people, I think this is quite important out there among scientists. They look for beauty in equations, and they say, oh, how beautiful the equation. And so it's like an art. They think that science is like an art. You look at something, it's beautiful, so it's got to be true. And equations are true in general, because they're tautologies. What's on one side of the equal sign is equal to what's on the other side of the equal sign. Great. It better be so, unless you made an error in your calculation or whatever, you put the wrong variable or whatever. But the point here is that these people are taking that one step further and says, oh, if it's beautiful, then it's science. And if it's science that is beautiful, then it's got to be truth. And again, truth means they're shoving it down your throat. I mean, they proved it to you maybe, but not to the guy, not to your neighbor. Okay, and that's where the problem comes in. And that's what's happening with QFT, quantum field theory. what they're saying here is, look, we can't explain gravity with quantum. We've tried for 100 years, we've been unsuccessful, and they realize they're unsuccessful because they can't pull with particles unless they do an inverse. They put a negative sign there for the negative momentum transfer, right? So they throw the ball, but it delivers negative momentum, and whatever object you threw it at comes towards you. You know, the pitcher throws it against the ball against the catcher, and the catcher, you know, runs up all the way to the mound with the ball in his hand, in his mitt. That's what they're saying. They're saying that you throw the ball and you pull the catcher. You know, very strange, weird thing. You can do that in mathematics. And can you do that in physics? Well, I don't think so. And so they couldn't explain it. They're sick and tired of not being able to explain it. So they said, let's move on to field theory, because general relativity is a field theory. And so now we have quantum field theory and general relativity field theory. Now with that word field, we can probably unite them both. And that's where all the efforts are today, to try to unite quantum mechanics, the classical quantum mechanics, the obsolete quantum mechanics, with general relativity through the word field.